to remind you on the SCL. Okay, so so what we can do, since we have this lecture, this Mali session or the practical session on Thursday and also on Friday. So you can make use of this Mali session to watch all these videos. All right. So it is 3 hours Mali session, right? All right. So a lot of time for you. Okay. I think probably some of you already watched the videos. All right. So and then I will giving you some questions that you can answer during this Amali session, right? So meaning that that will not take any of your other times to do this SCL things. So you can just use the Amali session. Apart from that, I also be giving you some questions, some extra questions based on the topic on this the last topic which we are discussing, this the surface reaction, and also the topic on the fast reaction which we're going to discuss today. All right, so that also you can do that during the Amali time, right? So please make use of the Amali time, right? The Amali session to do all this. All right, so I'll be giving you some the question. I'll give you some questions in this Putra Blast, so you can answer from there. Right, for group 1, I will ask Dr. Hanif to put the question in Putra Blast. Okay, I think that's it. What I want to say today. But so we're now going to this lecture. All right, so we have already seen the isosteric enthalpy. Okay, and we have tried to derive the equation relevant to this topic, where for the non-dissociative resorption, so we can have a fixed phase coverage, theta, fixed phase coverage theta, and for that fixed phase coverage, actually we can determine the value of delta H, which is the purpose of this part on the isosteric enthalpy. We can determine the value of delta H at any value of theta, meaning that the theta will be constant. So from this 1/2 equation, from the 1/2 equation, so we can do some derivation of the equation, a very simple derivation, and then we can get into the where did it stop? Can everybody hear me?
Yes.
Yes. Okay, thank you. All right. Okay, so from there we can do the derivation of the equation, and lastly what we can get is the equation of d ln p over d1 over t, right? This equation, and this is equal to delta H absorption over R, right? So and then from there, by plotting ln p versus 1 over t, as I shown you last week, we should be able to get the value of delta H. The value of delta H, this is the slope will be delta H over R. So the value of delta H then will be, you can get the value of delta H. So you can try the DIY question given. So this is, you can consider this as part of the exercise question given. So I have already given questions during lecture. These are all important questions, and you should try all these questions. And then we move on now to we have seen also this one, effect of exorbit mobility. So okay, so the exorbit mobility. So you can see that this is the questions of if we have a number of catalysts, which catalyst is the best to use for our reaction. So we have got to check. There are two things there. One is on the dissolvability of the exorbit or the reactants from the surface of the catalyst. The other thing is the diffusion, right? So these two process has to be balanced in order for us to get a good catalyst. As you can see from here, okay, so what is discussed here? Right, so catalytic ability of series of metals or shows a peak distribution. Moving across the family metals, the strength of bonds formed decreases, right? So as you can see, the strength of bond is decreases from left to right, right? From left to right, right? Which means that niobium has the strongest bond. Okay, meaning that so the adsorption process, but lower bond strength, on the other hand, increase the mobility of the species or the reactant on the surface, and so that the surface, the reactants can find a good surface for reaction to occur. If you have, for example, two reactant to react together, so they have got to move to the surface. One is to find the right surface for the reaction. The other is to for the two reactants to mix and react, right? So meaning that the catalyst or the surface has to allow the reaction to, or the reactants to move from one place to another for the reaction to occur. At the same time, has some absorptibility or low or some amount of dissolptibility, right? So these are all has to be balanced so that the reaction can occur, and we can get a good process to occur with good rate. Okay, so let's move on now. So the diffusion coefficient for migration over given plane obeys Arrhenius like expression. Okay, so this is given by this equation. This is for this is for the diffusion process. So the diffusion process. So you can see here for like carbon monoxide on tungsten. Okay, carbon monoxide on tungsten. So the diffusion of carbon monoxide on tungsten. So the energy of diffusion is given there, 57 to 87 kJ per mole, right? So it has to have a certain amount of diffusion energy, and then the diffusion coefficient, D naught, is 3.8 times 10 to minus 11 meter square per second. So, so the diffusion energy falls from 144 at low surface coverage to 88 at high surface coverage. So meaning that this diffusion coefficient or diffusion energy also varies with the surface coverage. So it varies with phase coverage, as you can see here. So from 144 to 88 at highest phase coverage. So we have got to also check this phase coverage in order for us to get a good diffusion, surface diffusion of the reactants on the surface, so that the reaction can be of good rate for us to get the product. So as you can see from the general rule is to have E diffusion over E desorption of between 0.1 and 0.2, right? So this is absorption energy of desorption, and this is the energy of diffusion. Okay, right. So kinetic of surface reaction. So catalyst provides an alternative reaction path with low activation energy. All right, so this is a known fact. Everybody know this, that we need catalyst for some reaction. Some reaction just cannot happen without catalyst. Some reaction occur at slow rate without catalyst. But with the catalyst, we can increase the reaction rate up to high level. And this is because of this what we call as the activation energy. Okay, for certain reaction, the activation energy is too high, so we have got to bring down this activation energy by introducing the catalyst into the reaction. Okay, so as you can see for this reaction, this is popular process also. This is the dissociations of Hi into H2 and also I2, right? So you can see this the reaction without this without the catalyst, the EA value is very high, right? 184. So you can do the reaction in a number of type of catalysts. These are metal catalysts used here, the gold and also platinum. Noble metal. These are called noble metal. Gold and platinum. Expensive metals. So as you can see, the rate of the reaction or the EA value can be reduced down to 105 and also 59, right? So with this EA value, so then the rate reaction will be faster, and then we can get the amount of reactants or the amount of product that we need in a fraction of time compared to if we do without catalyst, right? So the other one is the Haber process. I think everyone also is familiar with this process. And you can see that the reaction, this is the process where the reverse process actually the Haber process. So this is the process of splitting ammonia into nitrogen and also hydrogen. Okay, so you can see this process can be done without catalyst, but of course the EA value of the process without catalyst is too high, and the reaction will be very slow. Okay, and if we use tungsten as the catalyst, the reaction will be better, much better, less than half of the previous value without catalyst. You can see there, 162. Okay. kilojoule per mole for the EA value, so the reaction can occur very fast and you can get the product at the time at faster time limit as compared to without catalyst. Okay, so the catalyst does not affect the final equilibrium composition. So the final equilibrium composition will be the same. It only speed up the rate which the equilibrium is attained. So that's the function of the catalyst, right? So the catalyst actually speed up the process, and you can get the amount of the product, the same amount of the product faster compared to without catalyst, right? So as we can see, we are discussing on mostly on heterogeneous catalyst, and previously we were discussing on homogeneous catalyst. We were discussing on acid catalyst and also enzyme catalyst. The concept is the same, but on heterogeneous catalyst, the reaction occurs on the surface of the catalyst, where both catalyst and also the reactant are in different phase, right? So in this case, for example, you can see here the HI, okay, and also ammonia, right? So they are both in gas phase. They are both gas, right? So and so their product also gas, right? So their product also gas. So meaning that what has to happen here is that we have discussed earlier, the reaction has to go on with the absorption of the reactant, which is HI and ammonia on the surface of the catalyst, followed by the reaction, diffusion process, and so on, as we discussed earlier, and then the release of the product from the surface of the catalyst. Okay, so let us move on now to some mechanism on the surface reaction. Okay, so this is one, Lammer-Hiselwood mechanism. Okay, Lammer-Hiselwood mechanism. So the assumption of this mechanism is that the surface reaction is sufficiently slow, right? The surface reaction is slow, that the absorption equilibrium is not disturbed. Okay, so reaction occurs between species adsorbed on the surface, right? So meaning that the surface reaction has got to be rather slow compared to the adsorption, right? So meaning that the process occur where the adsorption occur on the surface, and the reaction occur through space reaction, space diffusion and reaction. Okay. So we go on with the unimolecular process, unimolecular decomposition. For example, we have decomposition of phosphine on tungsten, phosphine on tungsten, right? So this is the type of unimolecular reaction. Why? So because we have only phosphine, right? So only phosphine to the surface of tungsten, right? Only one type of molecule, right? So that's why it is unimolecular process, and the reaction occur, and then some process diffusion, reaction, and so on, and release of the product of the reaction. Okay. So okay, so this is the example of the process. This is shown in general mechanism. Okay. So we have the reactant, AG. AG is the gas, the reactant gas, absorbed on the surface or reaction occur on the surface. So the absorption occur, right? So where A is absorbed on the surface, meaning that from gas phase here, so it turn into the solid phase on the surface, and then after that, after the process occur, then we can see that the product is released. The product is released, and the surface is freed from the product, right? So we get back the surface. So that's why the surface is just the catalyst, right? So for example, in this case, if it is phosphine, then A is phosphine, right? And S is the tungsten surface, right? So then we can write the equation involved here based on the Langmuir adsorption process. Okay, please mind me for a while. I just a little break. Just a little break. Still people coming. Oh, I got to admit first, then only I can. Okay, come back to our lecture. Okay, so as you can see here, so the rate of the formation of the product, okay, the rate of the formation of product R will depend on theta. You can see here, will depend on theta. What is theta? Theta is the surface coverage, all right? Theta is surface coverage, and the surface coverage, according to the Langmuir equation, can be related to Kp1 plus Kp, where K is the rate constant for the adsorption. Okay, the rate constant for the adsorption. And K1, okay, K1 of course is here, okay, is the rate constant from the absorb situation, where A is absorbed on the surface of this on the surface to the formation of the product. So meaning that K then is if we consider this as three reactions occur together, K1 then is the rate constant for the third reaction, right? So the first reaction is the formation of the adsorbed surface, right? The second reaction is the desorption process, right? So the third one is the formation of the product. Okay, so then of course the reaction has got to be related to the formation of the product. Then dc dt then is equal to K1 theta. So we can write the equation as shown. K1 times Kp over. Okay, so this part is from the Langmuir adsorption process. So remember that we are using Langmuir adsorption process in order for us to explain the this mechanism. Okay, so low pressure regime, okay, low pressure regime less than 1 PA for spin at 1000 K is equal to then R is equal to K1 KP. So at low pressure, right? So at low pressure, meaning that this part is very low. Okay, so then 1 plus Kp is only 1. Okay, so then R just equal to Kp. Okay, so as you can see, so the reaction is of first order. And at high pressure, then P is very high. So 1 plus Kp will be Kp. Then reaction become zero order, where the reaction is only depend on K, not depending on pressure, meaning that the rate of reaction has become constant at that stage. So do we have, we don't have, as this is as we have seen earlier, or if we plot, if we try to plot the, okay, okay, so if plot R versus pressure, right? So what we get is that the reaction increase, and then it will be constant at certain stage. So right, so this is where it is first order, and this is where it is zero order, right? So as the pressure increase, it become zero order. Okay, so bimolecular reaction. So for bimolecular reaction, so there have to be two reactant. Okay, there have to be two reactant. So we have here this A and also B as the reactant. So they are actually competing to be absorbed on the surface. Only one type of surface because the reaction has to occur on one surface, otherwise they cannot meet, right? If it is a different catalyst, so they have got to occur on the same surface. So the reaction, the adsorption process occur, both get absorbed on the surface. So after the absorption of both reactants on the surface, then the reaction occur to form the product, which is still absorbed on the surface, and then the product then can be released from the surface in form of gas. As you can see there are 4 steps that can occur, right? So you can see the other one also as having another step actually, right? So this is where A absorbed on the surface, and the reaction occur where you get product which is also absorbed on the surface, and then the product is released from the surface. Or what can happen also here is that the product, after the formation of the product, it is released from the surface. This is not the reaction on the surface. This is on the gas phase. This is the reaction on the surface. So meaning that the product is released from the surface. You can add another step there. Okay, so for this type of reaction, so the reaction will have to depend on the surface coverage of both A and also B, right? So for the surface coverage of A, then it will be affected by B. For the surface coverage of B, it also will be affected by A, right? So that's why you have got a bit complex equation compared to the previous one, of course, because both reactant has got to absorb on the surface, on the same surface. So meaning that both adsorbate has to have to compete for the surface site on the catalyst, right? So the last equation is looks complex, but it is not that difficult to see. So what you have here is only one extra component here for both reactant, right? One extra component, which is this one is of course KBPB. The other one is KAPA. Right? So and then you times them together, and then you get the last equation for the rate of the reaction. So we need the rate of the reaction will depend on the partial pressure of A and B. On the partial pressure of A and B. So then we have got to know the partial pressure of A and B. So then at fixed PB, if PB is fixed, the rate is proportional to PA as small PA, right? So if we fix PB, right? So we need PB will become constant. The rates will only depend on PA at small PA, right? So meaning that this is constant, right? Okay, and then the rate is proportional to PA at small PA. So meaning that the reaction will only be depend on PA, right? So if PA is at large PA, at large PA, and so this is small PA at small PA. So the reaction will depend only on PA. So R will be proportional to PA. Okay, and then at large PA, it will depend on 1 over PA. So you can rewrite the equation based on this statement. So the rate increase with PA at the maximum and decrease as PA further decrease. Okay, so from there, as we increase PA, so the rate will increase, and if we decrease PA, the and decreases as PA is further increased. So meaning that the reaction, what will happen is that so you can see this is based on this statement. So you have the relation here where PA increase at small PA until the maximum. Okay, so it increases until the maximum, and then it will drop. So meaning that if you plot your plot of rate of reaction versus PA, which is the partial pressure of A. So what you can see is that the rate increase to a maximum, and then it will drop. Okay, based on this, so you can explain that from the equation given. So that is taken into account that we do it at fixed PB. So we can fix the PB. We can fix the partial pressure of B, and then just monitor what happened to the rate as we change the partial pressure of A. So, and then another one is consider the case where A is weakly adsorbed, then Ka is very far less than Kb. A is weakly adsorbed. So, meaning that the amount of A on the surface is much lower compared to the amount of B. So B is better absorbed on the surface, right? So because K is the equilibrium constant, K is the amount of absorbed equilibrium constant for adsorption. So A is then can be related to the amount of A adsorbed on the surface, okay, to the amount of A which is in gas phase, right? So this is at equilibrium. This is at equilibrium. Okay, so then if A is really adsorbed, then we can reduce the equation into just this equation, right? Okay, so because Ka is very small, so you can derive that from the previous equation. If Ka is small, then if Ka is small, so what will happen is that the direction will only 1 plus Kb Pb. So then we can have this type of equation. At high pressure, then R is equal to K2 Ka Pa over Kb Pb. Right? This will occur at high pressure. So high pressure. So what happens is that, so of course the value of KAPA, KAPB will be very large, right? Compared to 1. So you can further do the equation, and lastly what you get is that Ka, K2, KAPA over KB, PB. Okay, so try to do that. Okay, so this Langmuir-Sherwood mechanism is in fact a popular mechanism compared to other mechanisms. So almost all thermal biomolecular space reaction occur by this mechanism. However, there are also evidence that a few radical combinations occur at different mechanism, which is the following mechanism that I'm going to see. We call that as Elie-Riedel mechanism, or Elie-Riedel, or Elie-Riedel, or whatever. Okay, so you can pronounce it in whatever way that you like, because this is not a common name to us. But anyway, try to find how we can pronounce it correctly. So I just pronounce it Elie-Riedel mechanism. So the surface reaction sufficiently low. The rate of the surface reaction should be the rate of the surface reaction is sufficiently low. This adsorption is not disturbed. So this is the same as we see from the previous one. Okay, so the rate of the surface reaction is sufficiently low, thus the adsorption is not disturbed. So the reaction can occur between the adsorbed species and another reactant species in the gas phase. Okay, so as you can see from the Langmuir-Sherwood, so both species are on the surface, but in this case, one species is in gas phase, the other one is on the surface, right? Okay, so so here the general mechanism is shown here, where we have the reactant A is adsorbed on the surface, right? So the other reactant B react with the A, which is adsorbed on the surface, and B is still in gas phase, and it form the product. They form the product C, and then the surface is released from the product is released from the space. We can get back the product, the empty surface, which is probably at the same time still having A on the surface, but C is released from the surface. Okay, so then we can write the rate of the reaction, or dC dt, where C is the product. In this case, as if this, of course, will depend on the surface coverage of A, because A is absorbed on the space, and not the surface coverage of B, but on the pressure of B. Why? Because B in gas phase, right? So then the equation has become simpler compared to the Langmuir-Sherwood equation, because in this case it doesn't involve the space coverage of B. So A is not competing with B, right? A is not competing with B in this case. Only A is absorbed. Only things that A has to react with B, which is in the gas phase, right? And then the product is to be released to the gas phase. Okay, so X fixed PB, for small PA, so R is equal to K2 times KA PA PB, or R is proportional to PA, right? So fixed PB, small PA, small PA meaning that only the top part. Only consider the top part, because 1 plus KA PA is only 1, right? So for large PA, then 1 plus KA PA proportional to PA naught. Where is PA naught? PA naught is the saturation pressure of A, right? The saturation pressure of A. So if you plot the rate of reaction versus gas pressure, right? So you'll find that it's following almost a similar situation as you can see for the other mechanism, right? So where the rate of coefficient, or the rate increase, the rate increase, or the rate of coefficient here, the rate coefficient increase with pressure. So you can use rate coefficient or you can use rate, no problem. So the rate monotonically increases with PA and saturates at high PA, right? So this is the PA, right? So the rate increase with PA. So this is so PA. So we can use 0 to 1. Okay, the pressure of A here is where PA is 1, where the it saturates, where the rate coefficient is high, and it is also proportional to the saturation pressure of A, as we can see from here. Okay, so these are some of the examples of the mechanisms. For example, we have here is the reaction of oxygen and carbon monoxide on platinum, right? So you can write the mechanism. So oxygen on 111 surface of platinum, oxygen dissociate on absorption, while CO strongly can be absorbed on the surface, right? So what happened here is that oxygen dissociate, oxygen is absorbed on the surface, at the same time dissociates, and another one is carbon dioxide, carbon monoxide. Carbon dioxide also absorbed on the surface and very strongly absorbed on the surface through chemisorption. Okay. So if oxygen is absorbed first, its surface distribution is quite open, and therefore absorption of carbon monoxide is feasible, right? So oxygen can be absorbed first, and then we have space for the carbon monoxide to absorb. So the reaction may proceed by Langmuir-Hichilwood mechanism. So if the reaction is through Langmuir-Hichilwood mechanism, so we have oxygen gas absorbed on the surface, and at the same time dissociate, right, to oxygen atom, and carbon monoxide also absorbed on the surface, right, and then both the oxygen atoms and also carbon monoxide react to form carbon dioxide, and then carbon dioxide released from the surface. So these are the mechanisms that you can write based on the information you obtain from here, and based on your knowledge that the reaction is to occur by Langmuir-Hichilwood mechanism. Okay, so remember Langmuir-Hichilwood mechanism, both reactant react on the surface of the catalyst. So this experiment shows that the coverage time between carbon dioxide arriving at the surface and CO2 leaving is about in millisecond at 400 K. So since carbon dioxide absorbed only weakly, this long time is strongly evidence that the mechanism occur via strongly absorbed carbon monoxide species on the surface. So millisecond is considered a long time for the process. So which shows that in this case, carbon monoxide, we know that carbon dioxide is only weakly absorbed on the surface. So with that knowledge, so what happens is that carbon dioxide is actually make the reactions slower, right? Because of the strong absorption of carbon monoxide on the surface. Although carbon dioxide is only the reactant. Okay, so DIY show the reaction step if the oxidation of carbon monoxide occur by Illy-Riddle mechanism. Okay. Instead of Langmuir-Hichilwood, show if the carbon monoxide occur by Illy-Riddle, and which mechanism is more probable, if it's whether it is Langmuir-Hichilwood or Illy-Riddle, and answer why. Okay, so if you were to draw this what we call as reaction coordinate for the reaction, the energy versus the reaction coordinate, right? So we can see that carbon dioxide plus oxygen then absorb on the surface, right? Absorb on the surface, and then they have to go through a transition state before they form the product. Okay, and then the product is then release. The product is still absorbed carbon dioxide, and then release from the surface. So you can see the difference in the amount of energy when the carbon dioxide and oxygen absorbed on the surface. You can see that this the EA value for the reaction has reduced very much. Has reduced very much to very low value for the reaction to occur. Okay, synthesis of ammonia by Haber process. This is another popular synthesis that we have seen. So earlier it was not Haber process because that was the decomposition of ammonia to hydrogen and nitrogen. So the Haber process is actually the reaction of hydrogen and nitrogen to form ammonia. Okay, so this occur on this catalyst. This not very expensive catalyst. The metal oxide catalyst, which is iron oxide catalyst. Both reactants are absorbed and via dissociative mechanism. Okay, absorption of nitrogen is slow, though the activation energy is rather small. Pre-exponential factor is small because nitrogen is most likely absorbed and on initially and thus readily dissolved. Okay. So on the other hand, hydrogen much more easily undergoes dissociative absorption. Okay. And under the condition used in the synthesis process, so coverage of hydrogen is slow, but hydrogen atoms are mobile highly mobile on the surface. Okay, so you can see the mechanism. Hydrogen absorbed on the surface, at the same time dissociate to hydrogen atom. Okay, and nitrogen strongly absorbed on the surface and does not easily dissociates into atoms. On the next step, that nitrogen then is on the surface. So the dissociation occurs on the surface, right? So you can see absorption of nitrogen through activation energy is rather small. Pre-exponential factor is because nitrogen is most likely absorbed and on initially and thus readily dissolved. Okay, so this is the mechanism for what happened for this Haber process. Okay, so there are a little bit different way of absorption and this decomposition of hydrogen and nitrogen on the surface of iron oxide. And then the reaction occur, okay, on the surface to form NH. Further reaction occur to form NH2. So, and then another one to form NH3. And lastly, NH3 is released from the surface. Okay, so this is the mechanism that we can suggest for the process based on the information given, and you can work out for what is the proper discovery. Already informed you. This is both are absorbed on the surface, so it is issued by the Ramuel-Hishelwood mechanism. It should go by Ramuel-Hishelwood mechanism. Okay, let's take a few minute breaks. 1 or 2 minutes. Okay, for you to get some water, or for me to get some water. Actually, you are okay. Because you're only listening, right? Same time also you try to understand. You are focusing on the lecture, I believe. So this few minutes break will be also good for you to take some water, drink some water and so on. Do some stretching before we move on to another part, which is fast reaction.
Okay, Prof.
Okay, just stop for a while. Moving back to our lecture, right? Okay, let me just nice slide. Okay, so the next topic that we're going to discuss to finish up CHM 3103 is on fast reaction. It's a very simple topic. I think part of this topic has already been discussed by Dr. Hanif, I think, right? So the first part is quite simple, right? So the first part is only on the, okay, the experimental techniques for the kinetics. I think this is already discussed by Dr. Hanif. I think I don't have to go through this one. And also the sucrose measuring angle of rotation, plenochloride. These are some of the techniques used in chemistry for the for studying kinetics. Okay, on fast reaction, so we have a number of examples for fast reaction. Reaction occur in less than 10 seconds. That is considered as a fast reaction. Femtoseconds reactions. So, for example, we have ionic reaction. Acid-base neutralization is one of them, and that is considered also as fast reaction. So, although it is quite simple reaction, as you can see, you can do that in the lab or just normal reaction. The proton react with the hydroxide ion to form water. That is a very fast process. Okay, and then exchange reaction, for example, combination of aromatic amine and phenol. These are also very fast reaction. Reaction of oxygen and hydrocarbon. This is an explosion reaction. This is all a very fast reaction. Also, reaction of enzyme with substrate is considered a fast reaction also. Okay, hemoglobin and oxygen is also a very fast reaction, right? So otherwise you got to wait for some time for your oxygen that you have inhaled is react with hemoglobin to give you some sort of what process that occur in your body to give you energy and so on. And then metal complexation reaction. All right. So this is also very fast process. So there are a number of process which can be considered as very fast process. So how do we deal with the fast process like this? So what is important for us is to efficiently mix the reactant, otherwise we'll miss the process, right? So in order for us to be able to follow the process, the reactant has to be mixed efficiently, right? So the way to do is, for example, by using flow method. One way is by using flow methods, where reactants are mixed as they flow, and observation of compositional change along the reaction tube is equivalent to monitoring the progress of the reaction. So what happens is that we have got this reaction chamber where we have the two reactants in syringe, okay, in two syringe here, right? The reactants are both on in these syringes, right? So and then we'll press the reactant into a reaction chamber where the reaction will occur, all right? So the reaction will occur here, and then we can then monitor the reaction along these tubes. We can monitor the reaction along this tube, where you can move your spectrometer backward and forward to see what happened here, for example, what happened here, and so on. So at the very stage of reaction, then we can we can see the process. So meaning that the movement of the spectrometer has to be very fast in order for us to be able to check the process at different stage. Or you can also do it at certain fixed. You can also do at certain fixed position of a spectrometer by using another method. Because the disadvantage of this method is that you need large volume. You need large volume in order for you to be able to monitor the process along the tube. If you're a long tube, then you've got to have a very large volume. So the other method, which is to overcome that normal flow method, is a stop flow method. A stop flow method is where the reaction occurs in its chamber and the spectrometer is fixed at one position. Okay, so then the reaction occur. So after the reaction occur, this is the other thing are all the same. After the reaction occur, the reactant is the product. The reaction can be then monitored by the fixed photometer, which is placed close to the mixing chamber. Okay, so the reaction is controlled by another syringe, which is the stopping syringe. The stopping syringe, meaning that if you push in the syringe, you delay the reaction so that you can monitor the reaction by the fixed spectrometer, which is fixed on the chamber, close to the chamber, to the mixing chamber. So the reaction that can be monitored by this way is within millisecond to second. That is considered as very quite fast reaction. So the other first reaction is flash photolysis. So this reaction is very fast, and sample is exposed to a brief flash of light to initiate the reactions, and the content of the reaction chamber is then monitored, right? So the reaction is then the way the reaction is occur is just by give a flash of light. After the flash of light, then you have got to monitor the process, right? So this depend on the initiation process. So some reaction occur by this way, right? Some reaction, when you mix them together, they already react. And some reaction, you have got to initiate them by giving them, for example, the light, the electric current, for example, to start the reaction. So initiation can be done by laser photolysis, and then with pulse within femto to nanosecond, right? So femto is 10 to the 15 to minus 15 second, right? So very, very short. Nanosecond, you know, it is 10 to minus 9 second. So very short pulse, very, very short pulse. So after giving the pulse, reaction will start. So reaction occur in femto to picosecond. What is picosecond? 10 to minus 12, right? 10 to minus 12 second. Okay, and it can be monitored by electronic absorption or emission, for example, IR and Raman scattering. So you can monitor this reaction through this process, whether using absorption or emission spectrometer. Okay, so the spectra are recorded and following the excitation process, then we can then monitor the process. So example of this is, for example, this reaction, okay, of chlorine with HBr to form, this is reaction of chlorine with HBr to form HCl, right? So the reaction is start with a simple flash to chlorine. So chlorine then is dissociate or decompose into chlorine atom, dissociation reaction, right, to form chlorine atom, and then the chlorine atom will react with HBr to form HCl, which is in excited state, and then HCl in excited state then will will be de-excited into HCl by another body introduced into the system, which is M here. Okay, what is M? Depend. M could be another HBr, could be Cl, and so on. Or could be just another atomic species or atom or molecule that is introduced into the system to absorb the energy from the excited HCl to form HCl gas. And then we get M back into the system. Another one is a quenching technique. Okay, quenching technique is quite a simple technique. So a quenching method is how you stop the reaction after it occurs. So you want to stop the reaction immediately, and then at the same time you can analyze the content of the reaction mixture, how much reactant is left, and how much product has been formed. So that a number of ways that you can do that. Two popular ways is by chemical quenching and also by freeze quenching. Okay, so in chemical quenching, sorry. Okay, story for the disturbance. Okay, so the reaction is quenched by cooling the mixture within millisecond, and the composition is analyzed spectroscopically. So you can do chemical quenching. And in chemical quenching, just add reagent. In freeze quenching, you just cool down the reaction mixture, and then you analyze them. Right. So this that is chemical quenching. So another part is on the relaxation method. This is another way where you can study this fast reaction. For reaction in less in millisecond, the reaction is studied by slightly perturb the reaction which is in equilibrium. So what we do, reaction is in equilibrium, so we disturb the reaction, and then the reaction will then adjusted back into the new equilibrium. So as you can see here, right? So this is the reaction which is in equilibrium. Reaction is in equilibrium here, right? So at this point, we disturb the reaction. Okay, at this point, we disturb the reaction, right? So you can still not. Okay, we disturb the reaction there, and then after that, the reaction will respond. The reaction will respond, and then a process occur where we name that as the relaxation time before it reach the new equilibrium, and it reach new equilibrium, right? So then what we can do is to analyze this time, to analyze this what we call as relaxation time, and to get the value what we call as the value of tau, where tau is the value of the relaxation time. Okay, so you can see a bit of delay there. With your response on your screen. Sorry about that. I cannot do anything. Probably that is because of the internet speed. So perturbation is introduced by slightly temperature jump. What we can do is you can use a temperature jump, you can use pressure jump, you can use electric jump, any other way of disturbing the process, so that you can disturb the process and wait for the process to respond, and then measure the tau value, which is the reaction time between the first equilibrium and the second equilibrium, right? So according to Van Hoff, ln K is given by this. So a few degree of jump in temperature cause some change in the equilibrium constant. So you can see that the reaction depend on temperature, right? So you can disturb the reaction by changing the temperature of the process. You can change energy, you can change delta S, you can change R, delta H. At the same time, you can also change temperature. But of course, the easiest one is just by to change the temperature. Okay, and then the reaction is disturbed, and then you can then relax back to the probably because of too many slides. Then you can see that it is a bit of delay. Okay. Okay, so for example, if the reaction occur by first order, all right. So A to B, meaning that A is the reactant, B is the product, and the reaction occur by and then reach equilibrium, where K1 and K minus 1 are the reaction constants. And if A and B are in equilibrium constant, sorry, if A, B are equilibrium concentration, then actual concentration at time t can be written as A plus X and A minus X, right? So after we have disturbed the reaction, right? So after we have disturbed the reaction, so we can have this as not A, this is B, this is B, right? B minus X. Okay, so after we have disturbed the reaction, then the reaction will respond, and there will be change in the amount of the amount of the product and the amount of the reactant, right? So it will increase by X, B will reduce by minus X. Be reduced by X. So then we can write dx dt due to the response as you can see here. Okay, so dx dt is k1a plus x minus k minus 1 b minus x, because it is a direction of the formation of product B, right? So if the reverse one is, then it's minus k minus 1 b minus x. Okay, so you can then derive an equation, and that will give you this equation. All right. Okay, so dx dt minus dx dt then equal to k1 plus k minus 1 x. So then you can see here, like you can see there that x you can written in form or integrated form of the equation. So you are quite familiar with this. So the integrated form of the equation is this one, where k 1 k minus 1, you can relate that to the what we call as the relaxation time. So k1 k minus 1 will give you the relaxation time. So you got to then get the relaxation time. So you know that then you can get the from the value of k1 and k minus 1, you can get the relaxation time. So how to get the k1? How to get k1 and k minus 1? You only get k1 plus k minus 1. How to get k1 and k minus 1? Okay, this one I want you to think yourself. How do you get k1 and k minus 1 from the tau value? You already get the tau value, all right? You know the tau value, but what about the value of k1 and k minus 1? Interesting, right? Okay, so the next one is the second order reaction. Reaction also can occur by second order, where you can have A, B, reaction of A and B to form C, right? So here the equation a bit complex, right? So you have A plus X and B plus X, because of course if the reaction is disturbed, then both the concentration of A and B will change, and at the same time of course the concentration of the product. Okay, and you have you then can get this equation from here to here. I think there's no problem. Only you have problem from here to here, right? So one thing that we can neglect is this one, because x is very small. Because x is very small, then k plus 1 x squared is small. Then it can be then ignored. Can be removed from the equation, and then we are left with this. You are left with this. So one thing that you have got to see also, you have K1AB and also K1, K minus 1, C. So this is also removed from the equation, you can see from there, right? So how this are removed? How do we remove K1AB and K minus 1C? This one, I want you to think how this is done. Why you can remove K1AB and K minus 1C from the equation. Okay, so we are left with 1 over tau is equal to K1 AB, K1A plus B plus K minus 1. So you can of course rewrite the equation here. So dx dt is equal to this one. Then you can write the integrated form. Write the integrated form. Okay. So you can write the integrated form, and then from the integrated form you can get the tau value, right? So you can get the tau value. So from the tau value, then we can try plot. We can do a plot of 1 over tau versus the concentration of A plus B. And from the slope, we can get the value of K1. From the intercept, we can get the value of K minus 1. Okay. So 1 over tau versus the concentration of A plus concentration B. What are concentration A plus concentration B? A and B are the initial concentration. A and B are the initial concentration, so you can do that. So this is an example here, as shown here, the reaction of I minus and I2 to form I3. So we do not know what is the value of K1 and K minus 1. So we want to evaluate the value of K1 and K minus 1 from the reaction. Okay, so what we do is to start the reaction with a different initial concentration, as you can see here. So with different initial concentration, and then you let the reaction to occur, and you disturb reaction at some stage, and at each time you will get the value of tau. Right? So this is the tau value when you start the reaction with 0.57 and 0.36. You get 1 tau value. If you start reaction with a different different equilibrium concentration, then you get a different tau value and so on. Right? So with that, you can plot a 1 over tau versus the concentration of I minus plus I2. Okay, and you get a straight line, and from there you can determine the value of K minus 1 and K1. Okay, from the intercept and from the slope of the graph. Okay, so by doing so, they can get the value of K1 and K minus 1 as shown. So it is quite high value actually, K1 and K minus 1, right? So that shows that the reaction is going very fast, right? Okay. Last part is for you to try using the second order reversible chemical reaction of A and B was studied by relaxation method, and then AB react to form AB, and the relaxation time is tau, varies with the equilibrium concentration A and B as follows. All right. So you have the concentration, equilibrium concentration of A and B given there, right? And then you have the tau value, which is in nanosecond. In nanosecond, meaning that it is in 10 minus 9. 10 minus 9. Millimolar, this is millimolar, and this is nanosecond. So you can see 69 nanosecond, 35 nanosecond. So what you got to do is to determine the rate constant for the forward and backward reaction. So meaning that you want to determine K1 and K minus 1 of the reaction. All right. So now is the time for you to do that. This is quiz questions. This is quiz questions, and you will be submitting the quiz through Putra Blast. So you are given time from now until 9:59. Okay. So good luck to you. Have a good try, and please submit the answer before the time. So for group 1 and also for group 2. Okay. Okay, so that's it. That's all for the lecture today. Thank you very much for keep on listening to my lecture until today, right? So one last thing that you got to do is to do this what you call as penilaian pengajaran, teaching evaluation. So you got to go to the Putra Blast and do the teaching evaluation. Okay. So thank you very much. You can do the teaching evaluation for group 1. I think group 1 you do for Dr. Hanif and group 2 you'll do for me. Yes.